Hello, we are doing unsupervised learning. We already had covered up PCA, we had already covered up Gaussian mixture model GMM, and we had seen the PCA demo, right? In this session, we will take a new topic, but it is based on PCA. So what I'm gonna do is I'll compare two things and then I'll grab a new topic which is the non-negative matrix factorization, where it is based on the PCA itself. Okay, so I have to cover up a little bit information from the PCA. So what exactly happens in PCA, as I told you, that it is a method that rotates the data set such a way that the rotated features are statistically correlated with each other. Okay, and this is the meaning of PCA. What PCA does is it basically used to reduce the dimensions. But how it reduces the dimension? It rotates your data set in such a way that the rotated features, the new features that you are getting, are statistically correlated with each other. Earlier there is no correlation between your features. However, when you rotate, when you do your dimension reduction and you apply PCA, then you will see that your features are somehow, your principal components are somehow correlated with each other, and that's we want. Okay, so what it conclude, that it says selecting only a subset of new features. Okay, how we are getting this new feature? With the help of projection. Okay, subset of new features according to how important, how important they are for explaining the data. Okay, I hope you can see that we are taking new features. Okay, we are taking subset of new features, but how we are taking? We are taking how important they are used, how important they are for our data set. Okay, uh, so with the help of we are taking projection into consideration, and with the help of projection we are taking new features. But what kind of features we are taking? The important features which can be helpful in getting the good prediction or good classification. Just like inside the principal component, we need that it reduces the dimension in an extent that it gives you the best classification and prediction, also with the help of a lower dimension. Okay, so it takes it took care both of the things, that it reduces the dimension also, and it gives you good classification and good prediction. Okay, so this is the work of PCA. And also from the graph you can see that let me just change the color a little. So if this is the graph, then what exactly happens inside the PCA, that the principal component you will get is, let's say these are the two feature, feature 1, and I'll say this is x1, and this is feature 2, and this is x2. Then if these are the data points, we just precisely drawn it over here. There are so many data points, that means they have the larger information compared to the above part. Okay, so let's say this is the data point. All these are data points from the data set, and they are in the higher dimension. And what I need is, I need two principal component here. Okay, so let's say this is the center and this is my first principal component, and this is the second principal component. Okay, so let me say this is PCA2, or sorry, not analysis, this is just PC. Okay, and this is PC1. So what algorithm does is, the algorithm proceeds to find direction of maximum variance. Okay, and you can understand here that what is the first step in PCA? It will find the direction where the maximum information is available. Okay, and when I say maximum information, that means higher data points. Okay, higher dimensions. So what it gonna do is, it will take a vector space from here, and you can see these are the higher range data here. There's so much information available in this area, so it takes the arrow here, and this is known as your principal component 1. So this maximum variance is there, it is going to be your component 1, the principal component 1. Okay, and when I say maximum variance means uh, that is the contains most of the information. Okay, so PCA has given me two principal components, PC1 and PC2. The first PC1, it arrowed towards the maximum variance. Okay, wherever the maximum information or the most of the information available in that the area, it directed towards there. Okay, so this is the first step of PCA. Now it also concludes that it doesn't just not only the information, it also means that the features here, whatever the features we have here, features are mostly correlated with each other. Okay, this is also important. Not only they have higher information, but also the features in that area are very much correlated with each other. Okay, this is the first step, I can say. Let me just also put it over here. This is the first step. And what is going to be the second step? The second step is very similar to the first step, but what it's gonna do is, it will then again go to the data set, and it will find the next maximum variance. Okay, it will find the next possible the higher range of information where it is available in the data set. It will find, and it will direct towards it. But what is the direction? The direction is going to be orthogonal. Okay, when I say orthogonal, it means right angle. Okay, so it is going to be the right angle with perspective to the first arrow, and you can precisely see over here that this data is the next maximum variance, and it is completely right angle to the first principal component. Okay, this is the second step of the algorithm. It will find the other direction where data contains most information, but it will find the direction in such a way that it becomes orthogonal to the first direction, and you can see that right here. So I'll write it down here, that the algorithm, and this is going to be my second step, the algorithm finds the other direction where data contains most information but it will find the direction in such a way that it becomes orthogonal 90° to the first principal component or to the first direction. Are you getting this? I hope you are getting this. Okay, so the first step is to get the maximum variance and put your arrow towards there, and then the second step is the find the next maximum variance where the most possible valuable information available, but the direction is going to be the orthogonal to the first direction, that is 90° angle to the first principal component. So if I talk about only 2D, so when I say 2 dimension, there is only why only the two principal component, because and why only we have two directions only, because we are working with two dimensions here, and you had seen the graph, right? We had feature 1 x1 and x2, and we had seen that this is the direction, this is because only two possible direction we have in the two dimensions. So there is only there is only one possible direction, I mean for the second arrow, right? There is only one possible direction to have an orthogonal. Okay, so if this is the arrow here, then if I am working with two dimension, so if this is the two dimension, okay, this is x1 and this is x2, and I already have the center and I'm pointing this arrow over here, then I in two dimension I only have one possible way to create the orthogonal arrow, and that is this direction. Okay, maybe this is the other way I can do that, but maybe there's no available maximum variance is not available in this direction, so I cannot do that. So there are only two possible way, but let's say this is the only orthogonal, orthogonal direction, and this is 90°, and this arrow is orthogonal to the first direction, and that's why we have only one possible direction. However, you see here, however, your data set is not in two dimension, it is in higher dimensions. So however, in higher dimension there are many such orthogonal direction you get. Okay, so not only two, but you can get as many as orthogonal direction when you are working with higher dimension. So it depends on you that what kind of principal component you will take from those many orthogonal components. You will take you can take any, I mean you can take as many as principal component you want from this orthogonal directions, but here in this lecture I am taking two principal component for my two dimension. Okay, and so after this step, after getting these two principal component PC1 and this is PC2 and PC1, the next step is to transform this. Okay, next step is to transform it, and this is the work of actual PCA. Okay, so what I'm gonna do is you have this graph here, and this is my feature 1 and feature 2, but now instead of x2 and x1, what I'm gonna write is I will write here actually this is x1 here, and let me put x2 here back. So instead of x1, what I'm gonna write is I will write first PC, I mean principal component, and this is going to be don't confuse it with your personal computer. This is first principal component, and this is your second principal component. Okay, and now I'm going to use transformation, and you had seen this transformed function in your principal component demo also. So the earlier the data, it was something like this. This is the data. Okay, now I'm going to rotate this, or I'm going to move this using this transform function, and my data set now is going to be rotated in this way. Okay, it is centered around 0. So earlier your principal component looks like this, but now as I transform this data, your principal component is going to be in this way. It's completely 180 degree here, right? So I'm not going to I'm not going to, you know, I'm not going to draw this principal component over here, but instead I am going to just draw these data points that it has been transformed from 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 this, okay, from this to this. Okay, now your data set is being rotated in this way. Okay, so when you rotate this, then your first principal component aligns at x-axis, so this is your x-axis, and your second principal component and component analysis or component aligns at y-axis. Okay, I'll write it down here. It shows the same data, by the way. It shows the same. I need to change the color here. Just get back here, take the color, and first of all it shows the same data. There is no difference in the data at all. Shows the same data, and the second point, it rotated so that the first principal component aligns at x-axis and second principal component aligns at y-axis. Okay, this is the thing that we want. Also, I want to show you the original graph. So this is the original figure. You can see I have original data, and this is the data set, and these are the data points, and you can see that PCA give me the two principal component, component 2 and component 1, and this is my feature 1, by the way, and this is my feature 2. So this is nothing but your x2, or this is actually zooming, so that's why I cannot. Let me just change the brush here, so maybe this will work. So this, oh, I'm so sorry, I need to change the color, and I guess this will help me. Yes. Okay, I'll try my best to give you I don't know, this is my x x1 by this is my x1. Okay. Okay, and yeah, this is the original data that I was talking about. This is x2, x1, feature 1, feature 2, and the principal component, so PC2, and this is PC1. So you can see the first arrow, it is in the in the direction where high variance. So okay, this is the high variance, and the second principal component, it is orthogonal to the first direction. Okay, and this is the next high variance. So this is first, and this is second high variance. I hope you're getting it. And now the original data set is being transformed or rotated with the help of transform function. Okay, it has been rotated to 180 degree, and you can see still we have first principal component, second principal component, but it is like this. Okay, so you not instead of, but you can just assume that this is my x1 and this is my x2. Okay, these are features, but now the graph is basically on the this is basically the graph of principal component analysis. We have transformed the data set to 180 degree, and this is the high variance. You can see this area is of high variance. The same area is being shown over here. Okay, so the next high variance is in this location, and this is the same as this. I hope you're getting it. So the important thing that you have to understand, that the data is being centered around here. Okay, the data is being centered around here at this position, and you can precisely see over here that it is in the centered. Okay, which earlier it was not. Okay, your 0 is here, and here the 0 is somewhere here. Okay, your data is not centered, but now your data is being completely centered around 0. So in the note section, just write down here that before rotation How can I center this? Before rotation, the mean was subtracted from data. Mean was subtracted from data so that the transformed data is converted, or not converted but aligns to 0, actually aligns to 0. This is the thing that happens before rotation. Okay, I have to actually subtract the mean from my data set so that it aligns to 0, and this is what we had seen in the graph. Okay, so it aligns to the 0 by doing this. So this is my data set x of I, and I'm going to remove my mean from it. Okay, this is what I did. And when you do that, your data is going to be, very correlated with each other, and it aligns to 0. This is what I did. So what I did, if my xi is going to be my data point, then I'm going to subtract the mean from it. Okay, this is what I did. So the next point is, I'll say next point is, after this transformation, what I can do is, we have many, as I told you that in the higher dimensions you can get many principal components, but we have many such PC components, but for this lecture, only, but we can keep only few of them. Okay, so if you are having like 10 PC, like 10 principal component, using 10 principal component, you can use only 5 of them, and that is okay, right? So right now I have two principal component. I'm just sorry. Okay, I cannot use it. Oh yeah, if I have two principal component, then I can use only one principal component. Okay, so instead of using two principal component, I can use only one principal component. From this representation, you can see that I am again reducing my two dimension to only one dimension. This I can conclude, right? At least I can do that, right? So from two principal component, you are using only one principal component, 2D to 1D. This is what I said. And in the graph, the original graph, you can see this is what it looks like. So I have here principal 1 and principal 2, but now I'm using only one principal component. We don't have any y-axis. I had reduces. I just taken this transform data, this complete transform data, but I had removed the second principal component, and I get only 1D. So this graph is basically in one dimension. This is in one dimension, and this was earlier in the two dimension. So I reduces my dimensions from higher dimension to lower dimension with the help of principal component analysis. Using two PCA, I only had used one PCA. This is what you can see from the graph. Okay, this is one principal component, and we don't have any second principal component, but your transform data is going to be with respect to the second component that is being dropped. Okay, so this is the same data. We're just reducing the dimension. This is the same data, by the way. And now if you want to get back your original features, what exactly you can do is, if you want the original data, I mean data set, what you can do, you can get back that data with the help of, if you can again if you add your mean, so xi plus mu I, if you do the same thing, xi, your data points is again going to be plussed with your mean, then you can again back rotate, actually you can again back rotate, and you will get again your feature 1, that is your x1, and your feature 2, again you will get it. Okay, and this is the same data as the original data. You can see here, this is the data, and this is the data. They are the same. What you have to do, you just have to back rotate, but before back rotating, uh, you have to add your mean to the data point, and when you rotate it, make sure that you rotate with respect to the first component, okay, and you will get back to your 2 dimension again, but however you reduced earlier. This is your principal component analysis, and based on this principal component analysis, we are actually taking a new concept, that is non-negative matrix factorization, and it is very similar to that of PCA. And why I had taken this PCA again is, as I told you, that in unsupervised learning every topic is having a base, and base is like dimension reduction. And how you can do dimension reduction? I have 2 methods to do it. One is linear method and another one is non-linear method, and your principal component analysis is a dimension reduction method. It comes in linear methods itself, right? We have seen in the notes. So that's why before going through every topic, I have to take the base, and the base is PCA only, and that's why I'm taking it. So now we're gonna understand the non-negative matrix factorization. So I'll take the new page over here, and I will take the color, and this is going to be non-negative matrix factorization. Matrix factorization. Can't believe you. We have lockdown, still they are roaming around here and there. Okay, so we have NMF, abbreviated as NMF, and this is non-negative matrix factorization. So in the notes, it is another unsupervised learning, algorithm I hope you can see this. I think it is written properly. Another unsupervised learning algorithm which aims to extract useful information, and by means of the information I just want that it is nothing but my feature. It will extract the useful feature from the complete data set. So again, that by saying this, that it extract useful information or useful feature, by means of that, it is nothing but a technique called as feature extraction, just like your PCA. So this is a feature extraction. It is based on feature extraction method. So okay, so this NMF is a feature extraction method, again just like PCA. I'll write it down here, just like. So it works similarly as PCA, that is used in DR, and DR is nothing but dimension reduction. Okay, so I'm having a problem with dimensionality reduction. Okay, so this is actually very similar to that of PCA, that is used in DR. One more thing that I want to discuss is, if you remember your PCA algorithm, then as I told you that they have U, S and V, and it comes from the sigma. It comes from the this SVD, okay, singular value decomposition, and we had seen that it needs the covariance matrix sigma. Okay, so this is your covariance matrix. If you remember the algorithm, then this is the thing that we had discussed, this complete thing. Can't believe you. Okay, so this is my U, actually this is U, S and V, and this is your singular value decomposition, and this is the covariance matrix. This is what we discussed. So this SVD function will give you this 3 matrix, and I told you that U and V are orthogonal to each other. Now this u and v are nothing but your principal components. So this is going to be my PC1 and this is going to be my PC2. These are the orthogonal matrices, or you can say the vector spaces. Okay, so these are orthogonal to each other, u and v. And this S is basically the diagonal matrix, as I told you. So this three thing gives you the decomposition and the transformed data set that we talked about. Okay, this complete thing. So in the algorithm itself, it is given that u and v are nothing but orthogonal principal component that SVD is going to give you, right? And we had seen then we have reduced this u to from n cross n to k cross 1, I think. Okay, this is what we had seen. From n dimension to k dimension, we have reduced it, right? So your NFM is also very similar to that of PCA, and that is used in DR. Next thing is in the notes itself. So in PCA we find principal component, shortly abbreviated as PC, principal component. We find PC, principal component. They are orthogonal. That is, they are orthogonal, that we had seen in the algorithm itself. U and V, they are orthogonal, and where the variance is high. This is also important, where the variance is high. So this is for PCA, and now we will see that what happens in NMF. So in NMF, that is non-negative matrix factorization, where is it? Yeah. So it says that here in NMF, we want both component, that is the principal component, that we want both component and the coefficient of that component. Okay, the component, the coefficient, to be here, to be, the important thing is to be non-negative. This is the crucial part of non-negative matrix factorization, that here in PCA the crucial part is the orthogonal, here in the NMF the crucial part is non-negative. Okay, so your component and the coefficient of that component should be non-negative. That means if I say non-negative, then it means both should be greater than or equal to 0. This is what I meant. Okay, so you're in NMF, we want both the component, the principal component, and the coefficient to be non-negative. Here in the PCA, those components should be orthogonal to each other. That is the only difference. We only want that it should be non-negative or should be greater than or equal to 0. This is the NMF, and we will now discuss the complete non-negative matrix factorization. I just want to make it compare with PCA and the algorithm itself. And now we'll see the complete theory and whatever the representation I have for the NMF. Okay, so your non-negative matrix factorization is a group of algorithms. So NMF group of algorithm, a group of algorithm that is used in what you can say, the for the analysis of multiple data set, or you can say multiple variant, or we call it multivariant. Okay, I'm so sorry to not use that word, multivariant. It is a group of algorithm that is actually used for multiple variant or multivariant analysis, and in the linear algebra it represents in linear algebra where a matrix V is factorized. This matrix V is being factorized into two matrix. Let me take color to show these two matrix. Two matrix, one is W and another one is H. So we'll play with these three matrices, that is V, another one is H, and another one is W. And V is basically the output matrix, that is the factor matrices with the help of a product matrix of W and H. Okay, so it is the algorithm that uses, you can say, in the linear regression for multiple variables. So it uses actually in the multiple variable multivariant analysis, and in linear algebra we have, if we have a matrix V, then it is going to be factorized in order to get two matrices, that is W and N and H. And make sure that these the property with the property that these W and H, the property not only W and H but also this V. Let me go to here with the property with the property. This property is important, and you already know that what kind of property I'm talking about. With the property that all these three matrices, all three matrices have no negative element. This is important. In PCA we talk about orthogonal, however in the NMF we are talking about no negative values, or should be greater than or equals to 0. So these three matrices, we don't want any negative values, we only want positive values. Okay, and this property makes the resulting matrices easier to inspect. Okay, because of that property, the resultant matrix that we are getting, like V or any other, it is going to be easier to inspect. We can get a profound output from those matrices. Okay, and this NMF have the varieties of applications in the real world, or in not only in the machine learning, but it can also be used in such as, so I'll write it down here. Let me just change the color. Color is important. And I need an eraser, so this is, where is it? I think I lost my eraser here, so just okay. And now, so the applications, I hope you can see this. Next time I'm going to make it black. Applications of NMF, it can be used in the field of astronomy. Then it is used in computer vision, it is more useful in NLP, the text mining application. So that's why we have document clustering. Okay, so document clustering. It also very useful in audio signal processing. I need only positive values only, no negative values. So what I can get, I can get a smooth sine wave here. Where is it? Yeah, so I don't want this negative values. Okay, I only want this. Okay, so that's why this is useful in audio signal processing. It also used in the machine learning, so more precisely in the recommended system. Mm, recommended systems such as in Amazon, like it recommends something based on the product that you choose. So if you are selecting a cloth, then it will recommend you the other stuff based on the chosen cloth. Okay, it also used in bioinformatics. These are the practical applications of NMF, and if you are interested, you can go for these applications to work around. If you know the NMF, then you can work around in these field. Okay, and the NMF, also NMF in NMF. Importantly, we talk about V, W, and H. These are the three matrices which consist the complete NMF. So it actually looks like this. Where exactly I can draw? I can just yeah. So it looks like this. Yeah, where is it? I cannot see the cursor. Yeah. So your W is this. So it is going to be the matrix, and then it is going to be product multiplied with the H matrix, which is the coefficient matrix. Okay, and then you will get a factor matrix in the form of V, which is a linear combination of W and H. I hope you can understand. That means the column and rows is being what you can say, it is get linearly combinated with each other, and it is being outputted in this V matrix. So it is linear combination of the columns and rows of W and H. Okay, so this is the representation that I was talking about. V, W and H. I hope now you can understand, and we will see that what is the background that we can apply in the NMF. Okay, so let me just stop. So let's understand the background of NMF, and I was talking about V, W and H matrices. So let's V be the product matrix from W cross H. Okay, and you can represent that in this term, V equals to W H, and this V equals to W H is basically, so this basically the column vector. Okay, the column vector of this V, so I will write here the column vector. It is going to be represented as V of I. So this column vector Vi is the linear combination. It should be the linear combination. I hope you can see that. That is the linear combination of the component. So when I say component, it is nothing but W, and also the coefficient, and when I say coefficient, it is the H. Okay, so it is the linear combination of the column vector W using the coefficient of the column H. Okay, and I can write this sentence uh, in this way. This is hard with this pen, so I will write here that where is it? I again need to change the, yeah, I need to change the thickness. I cannot see the cursor over here, so this is okay for me. So what I can write is, I will write V of I equals to I'll say W for the component and H of I. Okay, and you can see this is the column vector, sorry, the N column vector for V, and this is the column vector, H of I is the column vector of H. Okay, so if this is the, oh, I'm so sorry. So if let me just put this bracket. So if your V looks like this, so if this is the V, then all these column are nothing but V of I. So this is V of 1, V of 2, V of 3. So in general this is V of I, and when I say H, so H is going to be like this. All these are H, so this is going to be H1, H2, H3, and so on to Hi. So I'm talking about these small v of I and small h of I. They are the they are basically, first v of I is the linear combination or the column vector of V, and it is the linear combination from the W dot Hi. Okay, so I can write this here. So I'm talking about this particular equation. So I'm writing here that again, right, where V of I is the ith column vector. It is the ith column vector of V, and this is a product matrix. We already know that it is coming from W cross H. Okay, it is the ith column vector of V, and small h of I is nothing but ith column vector, again column vector of matrix H. Okay, so this is the thing that we can derive from NMF. The next important thing here that we need to see is that the linear combination that you are getting here. Okay, so the when you are multiplying these matrices, the dimension that you are getting in the V of I or in the V matrix is basically lower than that of the product matrix that you are getting. Okay, so what I mean to say is that if your V is basically M cross N matrix, okay, if this is M cross N matrix, then I can say that my W is going to be like M cross P matrix, and my H is going to be P cross N matrix. And if you see, if you multiply these two things, you're actually getting nothing but M cross N matrix, which is nothing but V itself, right? But the idea here is that the factor, the dimension of the factor matrices that you are getting is lower than that of the product matrices. Okay, and this is the you can say this is the property that forms the basis of NMF. Okay, so I'll precisely write it down here that the dimension of the factor matrices, is lower than of product matrices. Okay, and this property forms the basis of NMF. Okay, so this you have to remember, and after writing this, please elaborate all these things in one line so that you can understand that if my V is M cross N matrice, then it is the W cross H, that is the product matrices, is nothing but the original matrix M cross N. Okay, if you are multiplying that, but the factor that you are getting in the VI is significantly lower than that of the the dimension that you are having in the product matrices. I hope you are getting it. And we can also visualize this whole thing, this whole thing that we had seen over here with an example. And I'll take an example of text mining application for NMF. As I told you that the NMF is precisely used in NLP application. So I'm also going to use that application to understand NMF. Okay, so I'm going to use text mining application. Okay, this is text mining application, and let's understand now. So let's say my input matrix that is to be factored, that to be factored is nothing but V. Okay, so this is the factored matrix that I will get from the product matrix of W cross H. This is my nothing but factor matrix. Okay, so V is here 1000 rows cross 500 columns. Okay, I'm getting this example from Wikipedia, and you can check that out resource too if you are not very clear with this example. I'm having an input matrix to be factored, that is V. This is capital V, by the way. So this V is having 1000 rows cross 500 columns, and let me bracket here and write row, and this is column to be more precise. And I can also say that my row in this particular example, my row represent word and my column represent document here. Okay, so my row represent word and my column represent document. That means we have 500 documents. That means we have 500 documents, as these documents represent column, and we have column 500. So that means we have 500 documents that is indexed, that is indexed by 1000 words. And because of this reason, okay, because of this word and document, this is nothing but you will get the application. Okay, that is the reason we are getting this text mining application. So we have an input matrix V having 1000 rows and 500 column. Row represent word and column represent document here. So that means, and precisely we can say that we have 500 documents that is indexed by 1000 words. And if I want to see it like visually, the matrix that I want to see visually, then let me change the color here, and I'll draw that matrix. So this is my input matrix V, and it looks like this. So these are the columns and these are the row. Okay, it looks like a matrix. So this is starting from V1, V2, and till where? Till V500. Okay, so these are small v, so it is nothing but v of I. Okay, that I was talking about. So we have 500. So here v, the small v represent, by the way, the small v represent document. And why document? Because the column here, you can see the column represent document, and if I'm indexing with small v, then this small v represent here nothing but document. I think you are clear with that. So going further with this, then you say that assume from the algorithm we want something. Assume from the algorithm we want something, and we ask something from the algorithm. So assume from the algorithm we ask to find the let's say to find 10 feature, okay, 10 new feature to generate 10 feature to generate let me just put it over here, to generate feature metrics, and what alphabet I use? I'm going to use capital W for that. I hope you remember this W. Okay, so here we are asking the algorithm to find 10 features. We are asking the algorithm to find these 10 features so that I can generate my feature matrix W, which consists of 1000 rows and 500 columns. Beside this, I want that it also finds me something called as coefficient matrix, and you are right that I will represent that matrix with the help of capital H, and I want that it should be, oh, I'm so sorry, I don't need this 500 here. Okay, but instead I need 10 feature, right? Because I had used this 10 feature because I asked the algorithm to find 10 features, and that's why the 10 features are nothing but column. Okay, this is a row and this is column, and if you see our data set, then the column represents the feature value, right? The column represents the feature value. So this is feature 1, feature 2, feature 3, and so I need to find these 10 features. So I have to provide 10 here for the column, right? Column represent feature, and that's why this is feature 10 feature. And in the coefficient matrix, what I'm gonna do is I want 10 rows and 500 columns. Okay, this is what I want from the algorithm. So it should generate a W for 1000 and cross 10, and it generates H as 10 cross 500. This is I want from the algorithm. Now if you analyze this thing here a little, if you analyze here, I just remove this because this is okay, and if you just change the color here, and if you analyze a little bit here, so my V, capital V, as I told you, it is M cross N matrix, and more precisely it is 1000 cross 500. Remember this, you already had seen this, but just for the sake of this example, I'm again showing you. And your W is M cross P, and this is 1000 cross 10, and H is P cross N, and this is 10 cross 500. These are the things that we had seen, right? And let me just go back here, because I have, so in the next slide, I hope you remember the previous note that V equals to M cross N, and W is equals to M cross P, and H is equals to P cross N. So what I'm saying here is the product of W cross H, this is multiplication, so product of W cross H is I'll write 1000 cross 10, this is my W, okay, this is W, and when I multiply it with 10 cross 500, this is my H. So what you will get, you are basically getting 1000 cross 500, and this is the same shape, is the same shape of input, is the same shape at input matrix. Input matrix V, that is 1000 cross 500. Okay, so you can see even I'm not getting any non-negative numbers here. First of all, this is the thing. Next is so W cross H, the multiplication, it is the linear combination. Okay, so from this 1000 cross 10 is multiplying with H 10 cross 500. So the V that you are getting is the linear combination of these 10 column vector. Are you getting this? So this, let me just point it out over here with the with the red color. So this 10 that you are getting here, when you will get V here, it is, this 10 is a linear combination. It is a linear combination here inside this V matrix. Okay, so I will write it down here. We can say that each column vector here, each column, no, this is each column only. So each column in W cross H. So when I say column, that means this is my column, right? And this is also the column. So each column in W cross H is a linear combination, of 10 column vector. And I think that you can draw something out from this. Okay, so this is the linear combination of 10 column vector. That is, you know, you are getting in the feature extraction also you had seen that from the independent variable you are finding 10 new independent variable, and those 10 new independent variable that you are getting is the linear combination. Okay, it is getting from the linear combination from the previous independent variable. Are you getting this? Okay, so the basis of NMF, we can consider each original document from the perspective of this example. Each original document is being built from a small set of hidden feature. Okay, so this is small set of hidden feature is nothing but our 10 column vector. Okay, this is 10 column vector, and these are nothing but 10 new independent variable that you are getting. Okay, so it is a hidden feature that is there in the data set itself. You just have to find with the help of some you know, with the help of some analysis, or by going through this PCA or an NMF. Okay, so this is the non-negative matrix factorization, and I think and I hope that you understand it. And if you have any doubt in this topic, you can you know, comment me in the comment section, or maybe you can mail me or do something like that. I'll be happy to help you. Okay, and thank you so much for listening to me.